Okay, so let's talk about the oxygen hemoglobin saturation curve because some of you are having a problem. So let me just draw it up here. Okay, now what we have on the x-axis, we have the partial pressure of oxygen, and this is the partial pressure of oxygen in the blood. Then here we have the percent saturated hemoglobin. So basically what this tells us is not how much each hemoglobin is saturated, it tells us how many of the hemoglobin molecules in your blood are saturated. So hence, the higher the saturation level here, the more hemoglobin molecules that are totally saturated or fully bound to oxygen. Now, there's two important PO2 values that we think of with the body, with the person at rest. One is 100 millimeters of mercury, and this value is important because this is the normal PO2 value of your arterial blood. Then we have a value of 40 millimeters of mercury, and this value is important because this is the PO2 of the venous blood, or the blood leaving the cells. Now when you look at the relationship of PO2 to the percent saturated hemoglobin, between 40 and 100, the curve changes something like that. And so here we have 100% saturation, here is 75. So just do that and put a percentage up there. So what you can see is that between 100 millimeters of mercury of PO2 to 40 millimeters of mercury of PO2, there is a change from 100% to 75% saturation of hemoglobin. So that means 25% of your hemoglobin molecules lose their oxygen. The remainder, the other 75%, are still bound to oxygen. So what does this mean? Well, if we go back and look here, this point here, 100 right here, this is the PO2 in your arterial blood. Or also, of course, it's the PO2 of the alveoli. So what happens is oxygen leaves the alveoli at the pulmonary capillaries, enters the blood, changes the partial pressure of the blood in the pulmonary capillary until it equals 100, and during that stage you load up your hemoglobin with oxygen. Then, as you travel through, the blood goes back, of course, to the left ventricle, and it's pumped from the left ventricle through the whole body. And when this blood here reaches the cells, the partial pressure of the cells is, or oxygen of the cells, is 40. So at this stage what happens is that because the partial pressure is down at 40, very quickly the partial pressure of oxygen in the blood supplying those cells also drops down to 40. And the reason why this is because, of course, oxygen moves down its partial pressure gradient, and as the oxygen enters the cell, the partial pressure of the blood drops, and so hence oxygen affinity for hemoglobin drops, and therefore hemoglobin starts unloading its oxygen. And so as you can see, between 140 here, over this period, it will unload 25% of its oxygen. Okay, so therefore 25% of the hemoglobin molecules in the blood leaving the cells are not bound to oxygen, whereas the other 75% are. So this gives us what happens in the normal cell. But let's now say if the cell is working harder. Now, when the cell is working harder, what's going to happen is it's going to utilize more oxygen because it needs that oxygen for aerobic metabolism. And so therefore the PO2 of the cell will drop. And let's say, let's say it drops down to 20 millimeters of mercury. Now, at 20 millimeters of mercury, the affinity for hemoglobin for oxygen has decreased even further, but it's decreased a lot more than what you'd expect. It actually will drop down, and let's say it'll probably be around 25% here. So what actually happens is that as the demands of the cells become greater and the partial pressure of oxygen moves down from 40 to 20, you can see there's much more dramatic fall in the percentage saturated hemoglobin molecules. So basically you're unloading here. I have the ability to unload twice as much oxygen than what you do to the normal cell. So when the normal cell is working and the PO2 drops, then what happens, of course, the affinity of hemoglobin for oxygen decreases so dramatically is that you can supply the cell with all this spare oxygen that you have once the cell stops working. So to summarize here, this area is the usage that you see in someone at rest. And so what it means is that we have this huge reserve of oxygen, a huge reserve of oxygen that we can utilize when our cells become more metabolically active. So when we're exercising, running, doing whatever, there's a heap of oxygen there that is ready to be utilized whenever we need it in order for the cells to be able to produce enough ATP via oxidative metabolism.